Hello everyone. Today we're going to look at inverse trig integration. So remember from earlier in the course when we did differentiation, the derivative of sine inverse was 1 over the square root of 1 minus x squared. We're going to do a slightly different form of it. We're going to do the derivative of sine inverse of x over a. And that's going to give us, with the chain rule and a little bit of algebra, 1 over the square root of a squared minus x squared. So if we use this differentiation, we go backwards, we get that the integral of dx over the square root of a squared minus x squared is sine inverse of x over a plus a constant. So this is going to be one of the main things we're going to use. We're also going to use the inverse of tangent, which is very similar. We get dx over the over a squared plus x squared. Remember that 1 over 1 plus x squared was the derivative of tan inverse of x. So again, we're going to do tan inverse of x over a. And because we don't have the square root anymore, we're ending up with an extra 1 over a here. So we get the integral of dx over a squared plus x squared is 1 over a tan inverse of x over a plus a constant. So these two things will be on the formula sheet just like all the other ones. So you don't have to have them memorized. You just have to remember when to use which one. So that's what we're going to do. We're going to do some examples. So the integral of dx divided by the square root of 16 minus x squared. So we have a square root, we have a number minus x squared. So that's going to tell us sine inverse. What we need to do is figure out a. So remember that 16 is a squared, so a will be the square root of 16, and it'll be 4. We're going to assume that a is positive, so we could also have a being negative 4, but for the sake of these, we're going to assume it's the positive square root. So all we have to do is replace in our formula a with 4. So the integral of dx divided by the square root of 16 minus x squared is sine inverse of x over 4 plus c. Now always remember, the really nice thing about integration is we already know differentiation. So I can always check this. I can differentiate sine inverse of x over 4 and make sure that it is mathematically equivalent to 1 over the square root of 16 minus x squared. You can always double check it by differentiating. So let's try another one. We have the integral of 3 divided by 4 plus x squared dx. So my denominator is a number plus x squared, so I should be thinking inverse tangent. And again, 4 is a squared, so a is 2. So when I integrate it, I still have the 3 from the numerator. And don't forget that with tangent inverse, I'm also taking 1 over a. So the 3 is from this 3, and then dividing by my a. So 3 over 2, tan inverse of x over 2. Now let's do some that's slightly more complicated. We're going to need some U substitutions, basically from here on out. So we have the integral of dx divided by the square root of 81 minus 25x squared. So we still have in the denominator the square root of something minus something squared. So we have to do a couple of things. First, we're going to figure out what a is. So again, a squared is the 81, which means a is 9. And now, again, we're going to do a U substitution. So I want U squared to be what else I have in there, which is 25x squared. So 25x squared is U squared. So U has to be 5x. So I square root the 25, I square root the x. So U is 5x. Don't forget the rest of the U substitution. Du is 5 dx. So when I do my substitution, I end up with a 1 over 5, and that's because of this guy right here. So 1 over 5 du is the dx. 81 is still the 81. 25x squared is the u squared. So that's going to give me still the 1 over 5. Sine inverse of u over a, which again is 9, plus c. And then I need to put back in what u is. So I end up with 1/5 sine inverse of 5x over 9 plus a constant. And again, I can always double check this by differentiating. Okay. Let's try another one. What about the integral of x over 1 plus x to the 4th dx? So again, my denominator is 1 plus something squared. Remember, anything to an even power I can think of as something being squared. So since 4 is an even number, it is something being squared. So a is 1, right? A squared is 1, which means a is also 1. U squared is x to the 4th, which means u is x squared. And remember, x to the 4th goes to x squared because I'm dividing by 2. Not because the square root of 4 is 2, but because 4 divided by 2 is 2. So u is x squared. Du becomes 2x dx, which is exactly what I need because I need to be able to get rid of that x that's in the numerator. So this is a good thing. So I will do my u substitution first. I end up with a 1/2 because of the 2 that's still there. So 1/2 the integral of du over 1 plus u squared, which becomes 1/2 tan inverse of u. Remember, I would be dividing by a here, but a is 1, so I'm not having to do anything. So it's just 1/2 tan inverse of u, plug back in what u is, and I get 1/2 tan inverse of x squared plus a constant. Okay. And again, I can always double check it by differentiating. So let's try another one. The integral of 3e to the negative t dt divided by 1 plus 9e to the negative 2t. Again, this looks like it could be a little complicated. The first thing you always want to check is this actually a natural log problem? So you always want to check, is the numerator the derivative of the denominator? So that's the first thing we should check by looking at this. But the derivative of my denominator will not be my numerator because of this negative 2t here. If I differentiate that, I'm still going to have e to the negative 2t, and I've only got e to the negative t up here. Okay, so it's not going to be natural log. So then I want to see, is it actually 1 plus something squared? So again, the exponent of my denominator is a multiple of 2. It's negative 2t. So it is something squared. So it's a good chance that it's a tan inverse problem. So again, a is 1, and then u squared will be the 9e to the negative 2t. If I square root that, again, I'm going to square root the 9, and I'm going to take my exponent and I'm going to divide it by 2. So u is 3e to the negative t. When I differentiate that, I get du is negative 3e to the negative t dt. And again, that means I'm on the right track, because ignoring the negative sign, it is exactly my numerator, which is what I want. Okay, so my next step is to do the u substitution. So don't forget the negative sign. I've got a negative sign out front. Everything gets substituted in really nicely. Again, I get negative tan inverse of u. Again, dividing by a is just nothing because a is 1, so I don't need it there. So negative tan inverse of u plus c, which becomes negative tan inverse of 3e to the negative t plus c. And yet again, I can double check it by differentiation. You really should get in the habit of checking it to make sure you did everything correctly, especially when there's u substitution involved. Okay, so we got another one. The integral of 2 cosine of 2 theta d theta divided by 3 plus sine squared of 2 theta. So again, the fact that I've got a number plus something squared in my denominator should tell you, let's try tan inverse first. Okay. So a squared is 3, which means a is the square root of 3. So a doesn't always have to be an integer. Okay, so in this case it's not, it's a square root of 3. U squared has to be sine squared of 2 theta, which means U is sine of 2 theta, so the squareds cancel. And again, it is U substitution. I need to differentiate this. So du is 2 cosine of 2 theta d theta, which again is exactly my numerator, so I know I'm on the right track. So when I do substitution, I get the integral of du divided by 3 plus u squared. And then remember again, with tan inverse, there are two a's involved, or two 1 over a's. So 1 over root 3, tan inverse of u over root 3, plus c. Plug back in what u is, and I get 1 over root 3, tan inverse of sine of 2 theta over root 3, plus a constant. Okay, so try them out. And remember from way back when we were doing the derivative, if I wanted cosine inverse, it's just the negative of the derivative of sine inverse. So we don't typically integrate and come up with cosine inverse because it's the same as sine inverse, just with a different sign on it, SIGN sign. So we're really only going to deal with sine inverse and tan inverse, so you don't have to worry about the other trig functions when it comes to the inverses. Okay, so try it out. Let me know if you have any questions, and good luck.